In this lesson, we're going to be using the periodic table to predict chemical formulas of when multiple elements combine. For example, NaCl, or BeI2, or Mg3N2. And this will make a lot more sense as we go. In the past, we've used relative atomic masses to predict chemical formulas. Here we have sodium and oxygen, which will combine into sodium oxide. Now say we also know the mass ratio in which sodium and oxygen always combine. That's 46 grams of sodium to 16 grams of oxygen. The relative atomic mass of sodium, which is approximately 23, tells us that each mole of sodium weighs approximately 23 grams. Now in our sample we have 46 grams of sodium, which is 2 times 23, telling us that this sample has 2 moles of sodium. If we look at oxygen, the relative atomic mass is approximately 16, indicating that each mole of oxygen weighs approximately 16 grams. Therefore, in our 16-gram sample, we have 1 mole of oxygen. So our chemical formula will show that for every 2 units of sodium, there's 1 unit of oxygen. And the way we write that is sodium with a 2 after it and oxygen with nothing after it to indicate there's only 1. Now what if we know the chemical formula first? Can we do the reverse process to determine the mass ratio? Let's try it with magnesium nitride, where we know the chemical formula is magnesium 3, nitrogen 2. Let's start with magnesium. This 3 in the formula tells us that we have 3 units of magnesium. Let's call that 3 moles. And our relative atomic mass says that each mole weighs 24.3 grams. So we'll multiply our 3 moles by 24.3 grams per mole. And that gives us a mass of 73 grams. If we treat nitrogen the same way, we see that there are 2 units of nitrogen, or 2 moles. And nitrogen's relative atomic mass is 14. So we multiply 2 moles by 14 grams per mole, and we get a mass of 28 grams. And now we have the mass ratio, which is 73 grams of magnesium to 28 grams of nitrogen. So yes, indeed, we can take the chemical formula with relative atomic masses and convert that into our mass ratio. Now we're ready to look at the periodic table, which contains all the necessary information to predict chemical formulas and mass ratios. Let's take a look. Here we have a classic periodic table, where the elements are in order of relative atomic mass from left to right and top to bottom. We're going to be paying attention to the vertical columns, and to make our lives easier, we're going to ignore the transition elements and look at this simplified table. You saw in this unit's video the pattern that Mendeleev discovered about how many times each element bonds with chlorine. From lithium to neon, there is a sequence where lithium bonds once with chlorine, beryllium twice, boron 3 times, carbon 4 times, then counting back down 3 times with nitrogen, twice with oxygen, and once with fluorine. Neon bonds 0 times with any elements. Then the next heaviest element, sodium, bonds once, magnesium twice, and the pattern repeats, which is why we put these next elements in a row lining up in columns of how many times the elements bonded with chlorine. Here are some examples of the chemical formulas that show this exact pattern. Lithium chloride, 1 lithium, 1 chlorine. Boron chloride, 1 boron, 3 chlorines. Chlorine oxide, 1 oxygen, 2 chlorines. And the second row follows the same exact pattern. Aluminum chloride, 1 aluminum, 3 chlorines. Phosphorus fluoride, 1 phosphorus, 3 fluorine. Okay, pretty cool. But what if we want to know about chemical formulas that don't involve chlorine? Well, it turns out that this pattern of numbers also tells us how often each element tends to bond with any other element. Let's look at lithium and fluorine. Both tend to bond with chlorine 1 time. And in fact, they bond with each other in a 1-to-1 ratio. How about beryllium and oxygen, which both tend to bond with chlorine 2 times? Well, it turns out they bond in a 1-to-1 ratio, which is the equivalent of a 2-to-2 ratio. How about boron and nitrogen, which both bond with chlorine 3 times? Well, it turns out they bond in a 3-to-3 ratio, or a 1-to-1 ratio of Bn. So, if 2 elements tend to bond with chlorine the same number of times, they will tend to bond with each other in a 1-to-1 ratio. You might be able to see where we can go from here. Let's take a look at elements from different numbered columns. Lithium and nitrogen to start. Now lithium bonds once with chlorine, and nitrogen bonds 3 times. Each lithium wants to bond once with other elements. Each nitrogen wants to bond 3 times. So for every nitrogen, you're going to get 3 elements that bond once to it. Therefore, we have 3 lithiums bonding to the 1 nitrogen. What do you think about beryllium and phosphorus? Beryllium wants to bond twice with other elements. Phosphorus wants to bond 3 times. So we're going to have beryllium and phosphorus in our formula. Because beryllium wants to bond 2 times, we need 2 phosphoruses attached. And because phosphorus wants to bond 3 times, we need 3 berylliums. And that's how we get the formula Be3P2. Let's try one more with aluminum oxide. Aluminum wants to bond 3 times with elements, and oxygen wants to bond 2 times. So those oxygens need 2 aluminums, and the aluminums need 3 oxygens. So we get the formula Al2O3. And you can follow this pattern to predict almost any combination of elements in the periodic table. Let's look at one more together, a common compound known as carbon dioxide. We know we're going to have carbon and oxygen in our formula. Each carbon wants to bond to 4 other elements, and each oxygen wants to bond to 2 other elements. So we would expect a ratio of 2 carbons to 4 oxygens. But you'll notice that this ratio could be simplified, because 2 to 4 is the same as 1 to 2. That's why the formula has 1 carbon and 2 oxygens. And the molecule looks like this, with 1 carbon atom bonding to 2 oxygen atoms. One last question. Can we determine the mass ratio in a compound such as carbon dioxide using the periodic table? Well, we have the formula and we have the relative atomic masses. We know that there's 1 unit of carbon, which has a relative atomic mass of 12, and we have 2 units of oxygen, which has a relative atomic mass of 16. So our mass ratio is 12 to 32. We can do it with any of these compounds. The mass ratio in aluminum oxide would take the relative atomic mass of aluminum, which is 27, multiply it by the 2 units of aluminum in this compound, and compare that to the relative atomic mass of oxygen, which is 16, times the 3 units of oxygen in this compound. So that gives us a ratio of 54 to 48. All of this valuable information is contained within the periodic table. Let's just take a brief look at all of the relationships we've learned in the past couple lessons. So Mendeleev used the relative atomic masses and the number of bonds to organize the elements into a periodic table. And the periodic table in turn can tell us the relative atomic masses and the numbers of bonds. It can also tell us patterns in chemical behavior, such as the fact that all the metals in the first column are not very dense and very reactive. We can also use the number of bonds to figure out the chemical formulas. And from the chemical formulas, along with the relative atomic masses, we can figure out the mass ratios. And as we did at the beginning, we can use the mass ratios and relative atomic mass to deduce the chemical formulas. Finally, the chemical formulas again tell us the number of bonds between each element. So all of these features interrelate, and together they form the foundation of chemistry.